couple of days ago, John Forbes told us that the winds are weak, and I give you evidence that the winds are actually weak even in the AGN where you expect them to be high. So this is the work I did for my PhD thesis with Sandra Faber and David Koo and others. So I'll summarize, and I'm in the job market, so in the fall I'll be applying. And since then my interests have expanded a little bit, so we can talk what I would like to do in the future. But here is a summary of what I did for my thesis. And mostly I focused on understanding the starburst AGN post-starburst connection. So in the earlier papers, I followed starburst from until they finally quench, and I showed that there is a significant delay of 200 million years between the peak of the starburst and when the AGN first appear. But we found that that the AGN seems to be enhanced in this recently quenched post-starburst, and we also followed our sample with CO observations, and we find that the gas fractions in these post-starburst galaxies is really high, but you see lower gas fraction only at later times. And in today's talk, I'm mostly focusing on the weak winds I studied in local post-starburst galaxies and high Z AGNs. So the question I really want to answer is, are the wind velocities of AGN significantly different from an AGN? And we also have seen the image of M82, this famous local starburst galaxy. So here I'm showing the famous bulge velocity dispersion black hole mass correlation, which may indicate that the coevolution of black holes and galaxies. And people have argued that this correlation may arise due to strong feedback from AGN. So here I'm showing the virial mass versus the stellar mass to the baryon mass from a simulation by Choi. So in her run without AGN are shown in black, and in her run with AGN feedback is shown in red, and the lines here shows you the abundance matching, and her simulations agree better with the abundance matching when she includes AGN feedback. So AGN feedback is an essential component of current galaxy formation models. And here is another example to show from the Horizon AGN simulation. In the odd numbers, I'm showing the runs with AGN feedback, and the even I'm showing the runs without AGN feedback. So without AGN feedback, galaxies form disk, and they are larger and massive. So they need AGN feedback to to correctly predict the mass and the size of galaxies. So this is just an introductory slides of what we should expect for AGN-driven outflows and starburst-driven outflows from Phil. So Phil tells us in his detailed models that if we look at, for instance, a warm gas, the warm gas only goes for supernova-driven feedback. It only goes up to 400 kilometers per second. And for the cold gas, it's a little bit less. So if we see something maybe higher than these velocities, that might tells us there is extra component due to AGN. And the question is, do we see that extra component? And here is just here I'm just highlighting what do I do differently in sodium D. Local galaxies have been widely studied. I'm just focusing on only on post-starburst galaxies and AGN, and I have also a large stack sample, and I also do a better job of matching my galaxies. So here is an example of my stack for the quiescent post-starburst galaxy. The data is shown in black, and in red I'm showing the stellar population model. So post-starburst galaxies are galaxies with no emission line, so we don't see H alpha emission. This is nitrogen 2. but we see strong hydrogen lines. That tells us these are recently pointed galaxies. So if I zoom in around the region of interest, sodium here, so what I see is the stellar population model doesn't do quite a good job of reproducing the data because there is extra component of sodium which comes from absorption due to ISM and also due to the wind. And I'm stacking 400 post-starburst galaxies. So here is my model fit of the wind. I fit two component model, one for the static component in the ISM, and the wind is shown in blue. So we see a wind of 350 kilometers per second. Even in the case where in these galaxies, there is no ongoing star formation, but there is wind. And there is also strong, you can see that most of the absorption line is due to ISM in the galaxy. So you can convert that by making some crude approximation and simplifying assumptions. There is a significant amount of gas in this system. So if this system have already experienced AGN feedback, you shouldn't actually see all this gas in these systems. So now I look at so those are quiescent galaxies. They don't have AGN, they don't have star formation rate. So I look at the corresponding, their progenitors that have AGN. So here I'm just matching by mass. Here is mass, axis ratio, redshift, D4000, indicator of age, H alpha and H beta, indicator of dust, and here is also WISE, indicator of dust. So these properties might affect the sodium profile. So I want to isolate the AGN effect from the star formation related effect. So that's why I do the matching. And if you are interested in these, you can read Chan's paper about this effect of all these quantity in the sodium profile. So if I now blow up in the sodium region of my stacked spectra, here I'm showing you my stacked spectra for AGN is shown in orange. The control data is shown in cyan. So this is after normalizing by the stellar population model. This is before normalizing. So what you see is generally there is a similarity between the profiles of the control sample and AGN, but there is a statistically significant difference between the two. So here I do modeling of the two populations. So here is shown for the AGN. So again, you see a blue shift due to the wind, which is 250 kilometers per second. The maximum velocity is 678 kilometers per second. For the control sample, you get a factor of 2 less in the wind velocity and the mean wind velocity and the maximum wind velocity. So even though there may be a difference between the wind velocities of AGN and the control sample, these winds are still weak. They are not like, they are not 500 kilometers per second or more. So that's a wind we detected in an absorption, which traces the cold gas. Now also the novelty of this work is people generally either study in absorption or emission. There are only a handful of actually galaxies, maybe 10 or so in the Sloan that people have studied both in absorption and emission. So here is, for instance, in my work, it's the first one that actually tried to study winds in absorption and emission in post-starburst galaxies and AGN. So here I'm fitting the O3 doublets with 2-component model. So the blue would be, a corresponding one for the moving wind component. So what I find is the mean shift is 200 kilometers per second. The velocity dispersion is 400 kilometers per second. In comparison to what I showed you before, so the average velocity shift are comparable, but the velocity dispersion is higher for the oxygen 2 component. And this is probably not surprising. If you look at the introduction distribution I showed you, the warm gas, as Phil predicted, is actually traced. It's more broader than the cold gas. But still, the problem is if you compute, again, assuming some simplifying assumption, very uncertain, what you get is the mass outflow rates are 0.2 solar mass per year. And the escape velocity, actually, the escape velocity, you can compute the escape velocity from the first component that's stationary. It's just like, it's generally 5 times the velocity dispersion of the orange component. So that's still 700 kilometers per second. The winds are, so the average velocity are much smaller, so the winds are not escaping. So here is the work I did. I'm not gonna go into details. Oh, there is also a paper we wrote about the gas. So what we learned from this is, the red is, so we studied the gas content of post-starburst and AGN, and compared them with the normal Sloan galaxies from cold gas survey. That's shown in black. So this is a cumulative distribution. So what we found is, compared to normal star-forming galaxies in the Sloan, the AGNs tend to show lower gas fraction at later stages, but the distribution is quite broad. So what that tells you is, if there is AGN feedback, it has to come at later stages. These AGN have quite a high gas fraction, so there is no feedback in them. So people also have tried to study winds in distant galaxy, but in distant galaxies, especially doing it in absorption, is hard. There are only a couple of works that try to study winds at d of 1 and beyond, or d of 0.5. So they quite disagree. So for instance, here I'm just showing the wind study from Alice Shapley's group. She was comparing Lyman break galaxies that are AGN, non-AGN, and she claimed there is this component at high velocity that she sees in AGN. So I try to do similar things, but at z of 1, and also now this time carefully constructing a control sample. So here I'm showing, in red I'm showing the AGN sample, and in black I'm showing the control sample. So what you see here is the mean velocities are at the order of 100 kilometers per second. Here is 500 kilometers per second. So we don't see strong winds in d of 1 AGNs. And the escape velocities again are 600 kilometers per second that we estimate from oxygen 2. So the winds are again at d of 1 too weak to escape and to quench galaxies. And here is just a zoom in of my the profile I showed you earlier. So I fit it with 2 components. The wind component is shown in blue, and the ISM component is shown in orange. So the velocities I infer are, as I said, are small, around at the order of 100. So again, you will see also here at d of 1, there is a strong ISM component. That also tells you there is still gas in this system. These galaxies probably haven't experienced the blowout phase that people claim exists. I'll skip this. Here are my conclusion. So my first conclusions are the AGN winds are weak, and they also are too weak to escape. And we see similar winds in star formation, in AGN and star formation, in star forming galaxies. And we find that there is strong ISM component, implying that there is still substantial amount of gas in the galaxies.
Questions? So what kind of luminosities are the AGN in your sample?
They generally tend to be low luminosity galaxies. So this is a plot of AGN bolometric luminosity versus the wind power, assuming some geometry. So my sample for the high redshift 1 is here. So they are low luminosity. And there is a correlation between, as you can see, there is a correlation between bolometric luminosity and wind kinetic power. But most theories predict actually is 5%, right? That's what you guys implement in your simulation. But most of the data, even from the other people, are roughly maybe 1%. And even the guys that are up here, if you look at these quasars that people have studied, the winds generally tend to be high velocity, but actually they are very localized. They tend to be less than 1 kpc in radius.
If I can just a clarification.
Yeah.
No, this is very nice work. And the clarification is just that, so a few percent was what was in a lot of the sort of first generation of models, but I think the landscape has gotten a lot more diverse. So there are certainly claims from ourselves and others that 10 times weaker in kinetic luminosity can still do a lot of work, and also that it's not necessarily clear that the winds are energy conserving. If they're momentum conserving, then as they expand, you'll get effectively, you can get arbitrarily low kinetic power, but still have them doing a lot of work. So just to make things messier for you.
I think one point I probably would like to clarify, if you look at these post-starburst galaxies that I showed earlier, I think that the idea you guys had previously was these guys experienced a quasar feedback. Even though you are seeing a low luminosity AGN in them, why do they still have gas? Unless you are going to argue that this gas is accreted recently after the blowout. So maybe the fact that they have a gas would tell you, even if they experienced quasar feedback, the quasar feedback didn't do much damage then.
Okay. Is it possible there's more mass in the wind, but just in a phase that doesn't show up? So warmer material that would be much harder to identify?
I don't know. In the intro slide I have from Phil, so this is what you should expect the distribution. So the hot gas should actually, in terms of mass, it should be less, and the cold. So we are probing the cold and the warm. So maybe we are getting the mass correct.
Well, I mean, I mean, I think it is generically true that you expect, whether it fits in with this, you would expect that if you've been trained more mass, like the really high velocity outflows might be very tenuous, right? Stuff that's slammed in, and if there's anything that's entrained a lot of mass, it might be going at quite low velocities just by virtue of having trained a lot of mass.
I mean, I think Tim Hassen would have the picture that in the starburst galaxy, what you're actually able to see is the cone that's the boundary layer where the entrainment is happening. It's actually a lot of mass flowing that's too warm to show up in the absorption for all the emission. And maybe the same could be true with the AGN. Not that a vested interest in rescue.
I mean, I think the challenge is you guys, the theories first reproduce what we observe, and then once that is done, we are happy to do more observations.